the sample size tends to infinity, that the sampling distribution of the sample mean tends to normality. So actually this can also be approximated using a Z-test and the Z distribution. Okay, so the key point here is this, is that is that we've actually got two possible tests that we can use here when the population variance is unknown and the samples are large. A more exact test would be the t-test. That's more exact. Okay, this would be a more exact test. Okay, where this z-test would just be an approximation. Okay, so it's only an approximation to the actual distribution. Okay? So just keep that in mind. And this is where some of the arguments always occur. They always say, "Oh, but look, my sample size is large." Even though I have an unknown variance, population variance, the arguments are always in here and fighting about which one is the most appropriate one to use. So the t-test is the most appropriate because irrespective of the sample size, if it's, let's say it's large, there will be an exact distribution to go along with the degrees of freedom. Whereas the Z-statistic is one, the Z-statistic is associated with the Z distribution, which is it's one exact distribution. It's not a family of distributions, and so it's only an approximation with respect to this particular size of the sample, but a more exact one will be the t-test. Okay, now what happens in the situation, right? So what happens in the situation where we can't guarantee that the populations have come from normal distributions? Okay, so we don't know, let's say that there's no evidence to suggest that the samples have been drawn from normal distributions. So what's the situation in these cases? Okay, so we've no evidence. We know that we either know the variance, we know the population variance, the sample size is small, but there's no evidence to suggest it's come from a normal distribution. We know the population variance, the sample size is large, but there's no evidence to suggest it came from a normal distribution. Also, the population variance is unknown, the sample size is small, and once again, there's no evidence to suggest that it's come from a normal distribution. And then the eighth case, is that the population variance is unknown, the sample size is large, and once again, there's no evidence to suggest that it's come from a normal distribution. Okay, well, let's just deal with this particular situation here. Once again, if the population variance is known and the sample size is large, irrespective of the fact that we don't know that it's been drawn, or that there's no evidence to suggest that's come from a normal distribution, the central limit term kicks in, and once again we're in the world of a z-test here. The central limit term saying that the sampling distribution tends to normality as the sample size increases, and hence we can use the z-test here in this particular situation. Let's have a look at this situation down here. Okay, once again, the population variance is unknown. The sample size is in fact large, but there's no evidence to suggest that the sample has come from a normal distribution. Once again, the central limit term kicks in, okay, which tells us that the sampling distribution of the sample mean is tending to normality, okay, as the sample size increases. So once again, we're in the world of a z-test. So the z-test can be used in this particular case. The important thing about the t-test is this, is that an underlying assumption of the t-test is that samples have been drawn from a normally distributed population. Okay? In the case of when things are large, irrespective of whether we can assume normality or not, you can see that we're in a situation of a z-test in all cases. But when we do know, that the sampling, that the population is normal, the most appropriate test actually to use is a t-test. The z-test is just an approximation. So what about the case where the population variance is known, the sample size is small, but there's no evidence to suggest that it's normally distributed? Now, the central limit theorem fails in this situation because the central limit theorem only works as the sample sizes get larger. So we can't rely upon the central limit theorem here. Okay? So in this situation, the test isn't a parametric test. It's actually some variant of a non-parametric. A non-parametric test is what should be used in this situation. In a single sample case, it could be the Mann-Whitney U test, okay, for example. Okay? Similarly, when the population variance is unknown, there's no evidence to suggest, and the sample size is small, and there's no evidence to suggest that the sample has come from a normally distributed population. Once again, where we are is we're into the world of a non-parametric test. Okay, okay, guys. Hopefully, this particular explanation, you can see that I have 8 cases. The reason why I have 8 cases is because I have 3 variables. Okay, so I have 3 variables. I have whether the population is 3 dichotomous variables, whether the population variance is known or unknown, whether the sample size is small or large, and one other condition, which is whether the samples have been drawn from normally distributed populations or whether there's no evidence to suggest that they've come from normally distributed populations. So in fact, what we have is we have 8 possible cases. Uh, this is hopefully as exhaustive as we need in relation to hypothesis testing and our decision in relation to whether to go for a Z-statistic over a T-statistic. Hopefully, this particular explanation has once and for all covered all possibilities, and hopefully that will demystify what's really going on and clear up the question that seems to be outstanding out there. Okay, once again, guys, this is Jonathan Lambert with Maths and Stats, and this video, another video in a series of videos dealing with hypothesis testing. I hope that was intuitive, and more importantly, I do hope that was helpful for you, and thanks for watching. Okay, bye-bye.